We're going to talk about the characteristics of the E2 reaction. This is elimination, order 2, and this is a reaction that competes with SN2 reaction. And it does it because we need to remember that a species such as, say, hydroxide, methoxide, etoxide, for instance, they are strong nucleophiles, but they are also strong bases. So we are going to classify that as strong base, strong nucleophile. So we will have the two reactions. These are two parallel reactions that compete. Strong base, strong nucleophiles. So we can have the two reactions happening. Typically also this is happening with polar aprotic conditions. Again, we need to remember what are strong nucleophiles, strong bases, and conditions to be able to predict products. That is our goal, and that's why we need to understand conditions and mechanism. So for this reaction particularly, the mechanism is concerted. And again, remember that concerted means that two things are happening. Everything is happening in one step. And we will have at the same time, we will have, say, a proton transfer. So the base here is going to attack the substrate and get a protons. So proton transfer with, at the same time, the loss of leaving group. And so let's do a little bit more of that. Say that I have the following substrate. Here I have, and here I'm using, again, this example I have been using for the other reaction. I have chosen a secondary alkyl halide so that I'm able to have this reacting under various conditions. Now, when we see a structure like that, we see that this is my alpha carbon, and we have two alkyl groups attached to, that is a secondary alkyl halide, and also we know this is, the configuration here is S. But in the case of the E2 reaction, since what's going on is the proton transfer base attacking to get a proton, and the hydrogens that are going to be extracted here are beta hydrogens. So we need to identify not only where is the alpha carbon, so next to that is the beta position. So we will have one hydrogen here, and we will have another beta position here. We will have three hydrogens here. So that way we're able to predict the product. So here we will have 1, 2, and 3 hydrogens. Let me erase that. That is a beta, so 3 hydrogens here. Now, when say that now I'm going to do the product, one of the products here. Another thing that's important here is the nature of the base. But let's see, all of these not only are strong bases, they are strong bases, but they're also small in size. That's going to be important for what we're doing next. So now, if we have, say, hydroxide, now we will have a proton transfer step, and then concerted at the same time. You're making a double bond here, and this is a part. So again, this is processes, proton transfer and loss of leaving group happening at the same time. What we are forming here is the following alkene. Now we're forming a double bond here, see, in this position, and you will have, let's throw it without the hydrogen, that. So double bond in this position where the arrow is, and you will have hydrogen and metal. This right here is a tri-substituted alkene. Now, what would happen if instead of extracting this beta hydrogen, the base gets one of these? In that case, I would create a smudge here. Okay, if it attacks on this one of these beta hydrogen, then you will form a double bond here. Let's remove this beta here. The one at the other carbon, this one here. We will have the H and let's say one isopropyl group. So this is the H. So in this, as we see here, no alkyl substituents on the side, only one here. So this is mono substituted. So now we talk about the fact that we need strong bases, but also the size is important. So what is observed in the E2 reaction is that small, strong bases favor the more substituted product. So this is favored by this bases. Small bases favor the more substituted, and this we're going to call the Zaitsev product. And the least substituted, this we're going to call the Homann. Why is that is important? Because depending on the base, we're going to get one product or the other. If you use small base, such as any of that, you favor then the more substituted product. If you use, say, a bulky base, say that you're using potassium through butoxide or triethylamine, those are some examples, then you prefer the least substituted product, so the Homann product. Again, we're doing this because we need to understand, see what the reagent is. And when I'm talking about the reagent, we want to look not only at the base or nucleophile, but also at the solvent. So here, pay attention that small bases then will favor the Zaitsev product, and the big bulky bases will favor the least substituted or the Homann product. And this we're going to be using in problems when we are predicting products. The fact that it prefers one position over the other to extract the hydrogen is called regioselectivity. And again, small bases are regioselective and we'll get the Zaitsev product, and the bulky bases are also regioselective, but you get the Homann product.